Okay, so for this video, we are doing the screen recording again because as with a couple videos back, I'm going to be hopping in and out of Desmos and I want to make sure that everything does record on the screen. So this lesson is transformations on quadratics and really everything else too. So we're going to study transformations for the first time as we're studying quadratics, but everything that we cover in this section is also going to apply to every other kind of function that we study. It's going to look a little bit different when you start changing the shapes. Not every transformation looks exactly the same, but they all essentially behave the same way. All right, so let me see if I can, there we go. So we want to start off with what is a transformation. I know this is covered in geometry. I know you guys see it in geometry. My classroom is right next door to a geometry teacher. I don't know how well it's always covered or what you remember or whether necessarily we're talking about it in the same way. So for the purposes of this class, we are going to define them. Basically, a transformation is a way of altering the graph by moving it on the coordinate plane or changing its size. So to go back to geometry, what I know you guys at least touch on is you touch on how to slide a figure like across the coordinate plane, maybe how to reflect it. I think you do rotations. We're not going to be doing rotations because if we rotate a graph, it's no longer a function. So it's not like rotations aren't a thing, but we don't do them algebraically. And then a dilation, which is essentially changing its size. So basically, we're going to be working with three of the possible transformations. We're going to be working with a translation. Translation is the very math word for like sliding. So we can slide the graph left and right or up and down. And if you combine them, it amounts to sliding it diagonally. We're going to look at reflections, flipping the graph over a line or axis. And there are a lot of different ways you can reflect these graphs. We're going to only explore one of those ways in this lesson, and we'll look at some of the other ways when we get to radicals. You can flip them over different axes. And then there are other ways you can flip them, like you can slide them and then flip them. And typically we don't do a whole lot of that in Algebra 2. You would do more of that in pre-calculus. So we lay the foundation here, and then for those of you going to pre-calculus, you would build on it. And then a dilation, which is essentially stretching or compressing the graph. Now in geometry, you might do this by scaling a graph up or like bigger or smaller. For us, it's really going to be like stretching it out. So we're going to do the vertical ones, but there are horizontal ones also, which again, like we do the vertical ones in Algebra 2, and then you can build on that doing the horizontal ones in pre-calculus. But it's almost like if you picture a shape in vertically and you pull it from like the top and the bottom and you like pull it and stretch it out. Or compressing it would be like you put your hand on the top and your hand on the bottom and you push them together. All right, now what we're going to do is explore these on Desmos. So the parent function, which was previously defined as the simplest kind of function that you can have in a family of functions. So the simplest quadratic function we can have is f of x is equal to x squared. And on Desmos, what we're going to be doing in class is we're going to be graphing each of these, and I'll have you guys graph them independently and explore and then like kind of summarize and reflect. So you're going to graph like basically the parent function plus 3, the parent function plus 5, the parent function minus 2 and minus 6.5. What do you think adding or subtracting a number outside the squaring does? And by that, what I mean is where the location of the adding or subtracting is outside of the squaring. So you have the x, the squaring, you finish the squaring, and then you add or subtract a number. And then you're going to summarize that in your notes, and we're going to summarize each part of this. If we add a number outside the squaring, the graph does, what? And then what you can't see because I cut the window off, but we can come back to it. Now you should be able to see it. If we subtract a number outside the squaring, the graph does what? Like, what is the graph doing? All right, so I'm going to click on over to Desmos, and we're going to start by typing the parent function, and I'm going to use y instead of the f of x just to kind of simplify things. And so that's my parent function that we have right there. And in my next line down, I'm going to type my first variation on that, which is x squared plus 3. And what we want to notice, well, I'll give you a moment to look at it. And what I have sometimes had students say is that, oh, the graph got skinnier. Well, it didn't really get skinnier. What it did do was slide up 3 units. So if you look at where the vertex of the original graph was, it was at 0, 0. And then we look at the vertex of the transformed graph, and we can see it is at 0, 3. So we have slid the graph up 1, 2, 3. Now, it's true that the parabola is narrower at the bottom. So when you have them nested like that, it might give the illusion like the other parabola is skinnier, but it's not skinnier. It just got slid up. So it's kind of fitting inside the bigger parabola. Now, the next one is y equals x squared plus 5. And what we want to notice there is that now the vertex has gone up 5 from the parent. And so we slid the graph up 5. The next one is y equals x squared minus 2, and we are seeing that the graph has now gone down 2, so 1, 2 spaces down. Now, at this point, you're probably seeing that there is a pattern here. This is not randomly throwing the graph wherever, that we actually can see what's happening. The last one is y equals x squared minus 6.5, and that's just to remind us that we are not constrained to integers all the time. And you can see that it went down 6.5 units. And so we can see that adding and subtracting a number outside of the squaring causes the graph to move on the coordinate plane in a predictable way. So I'm going to go ahead and delete those and come back to the PowerPoint. And you can take a look at that. So if we add a number outside the squaring, the graph goes up by whatever that number is. If we subtract, I'm sorry, it got cut off the bottom. If we subtract a number outside the squaring, the graph slides down. And I apologize for that. I cut off the screen so that it wouldn't necessarily show like the time and date and how many windows I have open. And it also manages to cut off the bottom of the PowerPoint. So I've got it. Hopefully it won't do that on all of them. Now on to the next. So this time we will look at what happens when we add or subtract a number inside the squaring. And you're like, well, what do you mean inside the squaring? Well, I mean this, where now we are adding or subtracting, but it's inside the squaring with the x. So we're doing x, we're subtracting 4, and then we're squaring it. So it's really an order of operations thing. Now we have something inside the parentheses. So we would take the x, we would subtract 4, and then we would square the result, as opposed to outside where you would square the x and then subtract 4. And you're going to do the same thing. Summarize what you found. If we add a number inside the squaring, the graph does what? If we subtract a number inside the squaring, the graph does what? There we go. Okay, so let's hop on over to Desmos. We're going to keep our parent graph there. We're going to use that for comparison. And my first one was y equals x minus 4 all squared. No, I did not square that. Let's try that. Oh, you know what? I'm trying to do exponents the way I do them in PowerPoint. There's a different keystrokes. Okay, now that might not be what you were expecting to have happen. And again, we're going to focus on the vertex of each, and notice that where you think, oh, minus 4, that should slide it to the left. It did not actually slide it to the left. It slid it to the right. Now, if you're like, well, I don't I don't know why. Like, why would that happen? If you recall back to a previous lesson, we graphed a parabola by plotting all the points. And we could do that this way. In fact, if I click on that and I click up here, I can click on create the table. Okay, and what you can see there is like literally if you take like a -2 and you plug it in, -2 minus 4 is -6, and -6 times -6 is +36, and it will literally put that point on the parabola somewhere. Okay, so I think, yeah, there we go. The point -236. If you plug in a -1, -1 minus 4 is -5, and -5 squared is +25. There it is. And we could go through that like for all of them, okay? And literally, if you just like plug in the numbers, you will see that it does indeed slide the graph to the right, okay? It's actually sliding it to the right, and it's sliding it to the right however far we, whatever the number is. So in this case, 4 units. Okay. Now, the next one is y equals x minus 2 all squared. And that one went to the right. So it goes to the right however many units we've plugged in. So if you do -4, it's going to go 4 units to the right. If it's -2, it goes 2 units to the right. Now, I mean, this might be the challenge one. So what do you think now happens if I add a number? So now you can almost get a glimpse of it right there. If you look at, now I haven't finished the squaring, so right now that's a line, but look at where the x-intercept is. So like even with that, you can tell that by like adding a 5, we actually, you could think of it, we went up 5 or we went left 5. But let's go ahead and put the squaring in, and boom, there we go. Okay, and so it actually went to the left 5. So adding the 5 on the inside made it go left 5. And the last one here is x plus 3. And as projected, that one went to the left 3. And so when we're working inside the squaring, we've got subtracting will make it go to the right, and adding will make it go to the left, which is what I call counterintuitive. It's not what you expect, but it is what happens. So coming back to our PowerPoint, if we wanted to fill these in, if we add a number inside the squaring, the graph goes to the left. If we subtract a number inside the squaring, the graph goes to the right, and the line is off the bottom on that one. I did have a fill in the blank, but the line's sitting on. I can see it, but you guys can't see it. Okay, so now we've explored some stuff. Now, for this one, predict where the vertex will be. Okay, so I want you to like consider that. Don't hop in and graph it yet. Just based off what we just did, where do you think the vertex will be? So we have x minus 3 all squared plus 2. Fill it in your notebook. And now let's go over and check. Okay, so we're going to go over and check. So this would be y equals x minus 3, all not cubed, squared plus 2. And we can look and see where the graph, the vertex is, and the vertex is at the point 3, 2. So there it is. And if you wanted to, you could like create a table for this as well, where it can tell you like what you could plug in and what's the point that would come out of it. And you'll notice that I can edit that. So if I wanted to put in, say, a +2 instead, I can do that, and you can see the point pop up right there. Okay, but there you go. So 0.32. So let's go back over to our presentation. And what I want you to do right here is actually do a little bit of reflection. So you have your answer right here, okay, whatever your answer is. And the right answer was the 0.32. So were you correct? Now, if you were, yay. Okay, that's awesome. We love to be correct. But if not, what was your error? So common errors that students make is getting the left right backwards. So you might have said -3.2. Okay, and in which case you would say, I went the wrong direction. I forgot that -3 would make it go to the right. Other common mistakes is switching the x and the y. So you might have said the 0.23 or to -3 or something like that instead of the 0.32. So you could, if you got it wrong, you might say your error was I switched the x and the y around. Whatever your error like happened to be. If you left it blank, then your error was I did not try. Okay, and that's the only kind of error that as a teacher I can't really work with. Is that you didn't try to do the problem. All right, so on to the next. So what about negatives? Like how are negatives going to work? So graph both f of x equals x squared and g of x is equal to -x squared. We want to observe what happened. And then now try these two. So try it with like a +3 at the end, what is going to happen there. And then summarize what you find below. If there is a negative in front of the x squared, the graph is going to do what? And where's my mouse? There it is. Discard. And here we go. So we've got y equals x squared, and we're going to type in y equals -x squared. And what we notice happens is that it flipped over. Now, if you stop and think about that for a moment, it does make sense. Where the original graph, when you're squaring something, it's always positive. Okay, so and then it goes down to 0 where it bottoms out. Okay, that's the only one that's not positive. But if you go ahead and you take all of those positive y coordinates and make them negative, they will flip over here. And so you've got all the same points, except now they're negative instead of positive. And then we'll try these two. Okay, so y equals x squared plus 3, which we knew was going to slide it up 3 units. So what happens now if I put the negative x squared? So that time it flipped it over and then slid it up. And you might be wondering, well, is there a way to get it to reflect over the x-axis? And yeah, and have it reflect like down, so it's down 3 units. There is a way to do that, and you could do that by like subtracting the 3 and then factoring the negative out. So we could get that if we did this. So if we did the negative and then we did the x squared and then the plus 3, okay, like that. So that would get it to reflect over the x-axis. We're not really going to mess around with that though. All right, so coming back to our summary slide. So what happened? Let's see, and what happened? It flipped or reflected over the x-axis. And then on this one, if there's a negative in front of the x squared, the graph flips over. We could also think of it this way. If it's positive, the graph looks like this. If you have a negative in front of that x squared, it flips the graph over. And you might hear that referred to as like it opens up or it opens down. There were a couple people on a recent homework assignment that were putting all that information on there, which I thought was odd, seeing as we haven't covered it, and also I did not ask for it. So don't do that. You guys know what you did. Don't do it. All right. So one last type. So this one is definitely the most difficult one for students to like express in words. We want to basically get a sense of what's going on. And then as you move ahead in math, you will get more precise with your vocabulary. So on the left, we have the parent function, f of x equals x squared. And we're going to compare that with if you have a 4x squared and if you have a 10x squared, and we want to see what happens. And the summary statement there where the line is cut off, it says if we multiply x squared by a number greater than 1, okay, if we multiply by a number greater than 1, so what will that do? And then on the other side, we're going to compare that with f of x is equal to 1/2 x squared or 0.1 x squared. What happens and if we multiply x squared by a number less than 1, because if you think about your parent, okay, that's a 1x squared. And so what happens if we make that 1 bigger? What happens if we make that 1 smaller? Okay, so let's hop on over to Desmos. And for the first one, we are multiplying by a 4. And what we notice is that the graph, there's a lot of ways you could express that. So I'll let you kind of think, like, how would you describe what happened? Right? You might think, oh, it got skinnier, it got narrow. All right, now let's see if we make, what happens if we make that even more pronounced. The 10 made it like even skinnier. Okay, so basically the bigger the number, I think of it as like increasing the slope. So just like if it were a line, if the slope were steeper, like you have a bigger and bigger number for the slope would get steeper and steeper. It's kind of the same thing that's happening here. You're making the slope steeper and steeper and steeper. Now we can go in the other direction. So what about a 1/2 x squared? Well, that made it wider. Okay, you could say wider, bigger, fat. I guess we could say fat. Now we'll do a 0.1. That's 1/10. And that made it even wider. So multiplying the x squared by a number would change the dilation. So this one doesn't move it on the coordinate plane, but it does change the shape. Okay, so we've got that going on. Let's go back over to our presentation. So if we multiply x squared by a number greater than 1, the graph, fill it in your notebooks. Like it gets skinny, it got narrow, and then if we multiply x squared by a number less than 1, the graph got fat, got wide. What happened there? Now, the previous two are the correct vocabulary for it is vertical. A vertical stretch, that's what makes it skinny, and a vertical compression, which is what makes it wide. And the way I think of it is this, like you've got your parabola, right? And then with your hands, okay, so this is your hand, all right? And okay, those are hands. They just trust me. And you're pulling on it, okay? And as you pull on it, it's going to stretch the parabola out, okay? You're going to pull it, and that's your vertical compression or vertical stretch. And then with the compression, all right, we've got your hand, all right? And this time you're going to be pushing. And when you push on it, it's going to like make it like get flat. You're almost going to like flatten it out because you're pushing down on it. As opposed to this one where you are pulling it apart. So we have vertical stretch and vertical compression, also known as making it wide. So on this summary slide, what I'm going to do is kind of recap everything that we just did. How are we doing on time? 24 minutes. Okay. So we got f of x, and I'm going to have an equal a. Okay. And this is kind of like generic. These are all the things that could happen. And here we go. So if there is a negative, it's going to flip it over. If you do not have a negative, it's not going to flip. All right. For your A value. If A is greater than 1, it's going to stretch your parabola out. If A is less than 1, it is going to compress your parabola. Now, I am being a little bit lazy on how I am describing that, because if you have something like -4, okay, out front, you might say, well, Miss Taylor, -4 is less than 1, therefore it should compress it. And in theory, the way that I'm phrasing it, you would be right. But remember, I said I'm being lazy about it. And we're not going to think of that as a -4. We're going to say the negative flips it. And then we're only going to look at the 4, and we're going to say that the 4 stretches it. So we're going to think of those as being two different things. Now, could I phrase that in a way that wasn't lazy? Yes. It's also very, very cumbersome. So you have to talk about the absolute value of A, or the magnitude of A is less than 1. Then it, compresses if the magnitude or absolute value of A is greater. And so it introduces this whole like absolute value element to it, which is just like really, really clunky. Okay. All right. Now the H value. So what about that H value? The H value is your left and right. If it is a positive in there, it's going to go to the left. If it is a negative, it is going to go to the right. And then lastly, your K value, if it is positive, it is going to make your graph go up. And if it is negative, it's going to make your graph go down. Your exponent right here tells us it's a quadratic. It is telling us the family and that it's going to be a parabola. It is not a transformation, okay? And I have lost track of how many times over the course of the years students have tried to use the 2, and they're like, what does the 2 do? It tells us it's a quadratic. That's how we knew it was a quadratic in the first place. Okay, so if you're being like not doing what you're supposed to be doing, and you're like, I'm just gonna listen to this video, you need to write this down. Like if you didn't write anything else down, write this down. Okay, just write this part down. All right, so example problem. So when you are asked to state, oh gosh, I hate typos. State the transformations. You are being asked to describe how the graph has moved or changed. So every year when I get to questions like state the transformations, I absolutely will have students that try to like solve something. Like I've seen the wildest things, quite frankly. And like it's like we're really not understanding the directions. So if the directions say state the transformations, this is what you are being asked for. And here's how you would answer it. So for this first one, you would say it is stretched, okay? And the reason you know it is stretched is because of that 2. You would say it goes right, and then you're going to tell me how far, okay? And you know that from the -3. And then you would say, look at the 4, and you would say it goes up 4. And that would be your answer. Stretched, right 3, up 4. Now, you could give more information on the stretch. So you could say stretched by a factor of 2. But that is maybe for your next class, okay? Like stretched by, and then you get into more depth with how it is stretched. All right, for the next one, here is how you would answer it. You would say it is flipped, okay? And the reason you know it is flipped is because of that negative. You would say it goes left 4. The reason you know that is because of the +4. And you would say it goes down 1 because of the -1. And that is your answer. It should not take you a whole lot longer than it took me. When you were first stating the transformations, you might have to look up that little summary that I gave you, or you might want to hop into Desmos and take a look at it. Okay, those are all things you might want to do. But once you get to the quiz, you should have done enough of them that you're not thinking super hard about them. All right, this last one, you would say it is flipped. okay, and we know it's flipped because of the negative, you are going to say it is stretched, not compressed. Okay, I know -3 is less than 1, but we're using the negative to flip it, and then we're just looking at the 3, and then we're going to say it goes up 2. Now, the common mistake on that last one is students get so used to seeing all the transformations that if you're missing one of them, I have students like make up stuff. Okay, so we don't want to make up stuff. There is nothing happening inside the squaring. So there's no parentheses. That means there's no left, right. So you don't want to make something up, okay? We want to pay attention to that. So that's what we mean by state the transformations. You should not be giving me a number. You should not be solving stuff. You should not, like, this is what it means to state the transformations. So that brings us to our practice set finished for homework, and I'm glad the whole thing did get on the screen, although we have typos. I swear it's my computer keyboard. In fact, I can't even use like the touchpad mouse click thing anymore. I have to use a regular mouse because it's just not working. So anyway, for problems 1 through 5, state the transformations on each of the functions below. Use the parent function as your starting point. That's what we've been doing, okay? So it's just like the ones I just did, okay? So you're going to state the transformations. For problems 6 through 9, state where the vertex will be without graphing it, okay? So I want you to look at that. Look, is it going left, right, up, down? Like, what is it doing? For the vertex, you actually don't need to know if it's flipped or if it's stretched or compressed. That does not change where the vertex is. So only left, right, up, down, and you're going to state an ordered pair. So for those ones, your answer is going to be an ordered pair X, Y, okay? Just not with an X, Y, with numbers in them. And then for problem 10, oh, I love how that skipped lines there. For problem 10, this is like your kind of your challenge problem. You may not leave it blank. You may not leave it blank. You may not leave it blank. You're going to use f of x equals this right here as a starting location. So what I would do is I would go onto Desmos and I would graph that and see where it is. Now, to get from there to, and I'm sorry about that. That got like, yeah, that should be g of x is equal to x minus 5 all squared minus 1. Okay, that's your ending location. What transformations would you need? Hint, look, not lock. Okay, that's look at the vertex. So are you going left? Are you going right? Are you going up? Are you going down? Are you having to flip it over to get to the new one? So try that. Okay. I would graph both of them and I would count it out. Like, where am I starting? Where am I ending? All right. So that's everything. I'm sure this was, a little bit over 30 minutes. It's a little bit lengthy, but you are getting all the Desmos in there as well. As always, you guys know where to find me if you have questions. And so I hope to see you in class.